You probably heard the news earlier this week. There was an explosion on the surface of the sun, a solar flare, and because we at Science Friday want to know how everything works and why, we're calling in a couple of experts to explain the ABCs of a solar storm and actually how the sun works. How good are we at predicting these solar explosions? What effects can they have on the Earth? Are there still some unsolved mysteries about the sun and how it works? Let me introduce my guest. David Hathaway is a solar astronomer at NASA's Marshall Space Flight Center in Huntsville, Alabama. Welcome back to Science Friday, Dr. Hathaway.
Thank you, Ira.
You're welcome. Doug Biesecker is a physicist at NOAA's Space Weather Prediction Center in Boulder. He joins us from radio station KGNU in Boulder. Welcome to Science Friday, Dr. Biesecker.
Thanks for having me on the show, Ira.
You're welcome. David, can you give us a play-by-play of what happened there on the sun this week?
Yeah, it starts with a flash, a solar flare that we see particularly in X-rays from the sun, that the sun gets 100 to 1,000 times brighter than normal in X-rays from a sunspot region. With that, we saw that, of course, in the time it takes light to get from the sun, so 8.5 minutes or so. Mm-hmm. Within an hour, we saw radiation from it. This is energetic subatomic particles, electrons and protons and so forth. And that built up pretty steadily and stayed high for days. That whole explosion, it's a magnetic explosion on the sun, launched what we call a coronal mass ejection. This is literally 1 billion tons of matter moving at 1 million miles an hour, streaming through the solar system, and was aimed pretty much right at us. That hit us a couple days later and produced some spectacular auroral rays.
Mm-hmm. And is it going on still? Is there still activity going on?
Well, it's interesting you should ask. That one has since calmed down, but we are at this moment in the midst of an even bigger flare as far as X-rays, but it's off the edge of the sun, so we're not going to get the dramatic fireworks here on Earth from it. But we are at this moment in the midst of an X-ray flare that's even more powerful than the one from a few days ago.
Wow.
Ira, in addition to that, I just want to point out that the radiation storm is also in progress.
So we called you at the right time today.
Indeed.
All right, we have a whole bunch of time to talk about it. So 1-800-989-8255 is our number. We're going to talk about this new solar flare that's happening as we speak, and bigger than the one that happened earlier this week. You can tweet us at SciFri, at SCIFRI, and you can also go to our Facebook page and our website. So we'll be back talking more about solar flares with David Hathaway and Doug Biesecker. Our number again, 1-800-989-8255. We're in the middle of a big one, and we'll talk about it some more. Stay with us. You're listening to Science Friday. I'm Ira Flato. We're talking about solar astronomy this hour with David Hathaway of NASA's Marshall Space Flight Center, Doug Biesecker at NOAA's Space Weather Prediction Center. Our number, 1-800-989-8255, and we called them up originally to talk about this week's earlier solar flare, but we find out right now, as we speak, there's an even bigger one happening, although not the one that's pointed at us. It's not going to be hitting the Earth. Is that correct, Doug?
Right. So the active region, these regions of intense magnetic field that produce flares and give us the coronal mass ejections, the same region that gave us the activity earlier in the week has rotated in the 5 days since to where it's now seen at the edge of the sun. And so the coronal mass ejection associated with this big flare is headed off away from Earth. But even in spite of that, we see the direct X-rays and ultraviolet from the flare, and any radiation being accelerated by the coronal mass ejection can still make its way to Earth, and we're seeing both of those effects in progress.
And what effect would it have on Earth here?
Well, the flare, the main effect is an atmospheric one. And the way you might be concerned about that, well, really, you probably wouldn't be, but if you're somebody that uses high-frequency radio to communicate, say a ham operator, or you're in a ship at sea, or you're even in a plane flying, across the Pacific Ocean right now, you'd find your high-frequency radio probably isn't working because of this solar flare. The way that works is the signal has to bounce off a layer in the atmosphere known as the ionosphere, and right now the ionosphere is very different from its normal state, and that bounce of the radio signal doesn't happen. It in fact gets absorbed by the atmosphere. So HF high-frequency users in the Pacific right now are feeling the effects of this solar flare.
Were they warned about this one?
Well, predicting a solar flare would have happened today at 1:37 Eastern Time. We're not there yet. What we do is we look at these regions of intense magnetic field, the sunspots, how many of them are there, how complex is the magnetic field contained within, how big is it, and from that we can compute a probability. So much like you might hear 40% chance of rain tomorrow, we can also say 60% chance of solar flares tomorrow.
So people in that area that you're saying, pilots, whatever, who are flying, they may be having trouble and not knowing why, but probably predicting, another solar flare.
That's exactly right. But they have a workaround. As long as they can see those communication satellites that sit over the equator in geostationary orbit, 22,000 miles above the surface of the Earth, they can switch to that SATCOM and still get the signal through.
David Hathaway, what is it on the sun that causes this thing to happen? What's going on in the internal workings of the sun?
It's magnetism, pure and simple. That it's magnetic fields involved in all of this. It's magnetic fields that make the sunspots themselves. That within the sun, the flow of these ionized, electrically charged gases produces intense magnetic fields, and in sunspots it gets to be, thousands of times stronger than the Earth's own magnetic field, strong enough that, in fact, it chokes off the flow of heat from inside the sun, which is why sunspots appear dark. But those magnetic fields can get twisted out of shape and basically short-circuit by reconnecting, and all that magnetic energy gets released explosively. And so that's where it ultimately comes from, is magnetism ultimately produced inside the sun, that we see manifest at the surface in sunspots and above the surface in coronal features, these loops where the gases in the sun's hot corona are confined to move along these magnetic loops above the surface, and so we can see the presence of the magnetic fields there. But it's again, magnetism's the key to it all.
Speaking of magnetism, does our Earth's magnetic field that surrounds it, does it protect us from any of these things?
Very much so, yeah. That the Earth's own magnetic field would normally look like a bar magnet's magnetic field, what we call a dipole field, going into the north, coming out of the south. But because it's also subjected to the solar wind that blows off of the sun at 1 million miles an hour, that solar wind drapes the Earth's magnetic field into a comet-like structure, a tail. So it pushes the magnetic field on the day side closer to the Earth, and it stretches it out on the night side into a long tail and back of the Earth. So that magnetic field does protect us from charged particles, but it can also get disrupted by the magnetic fields in these coronal mass ejections. That when this magnetic explosion goes off, the coronal mass ejection that's produced has magnetic field is a key part of it, and that magnetic field, once it hits the Earth, if it's directed in the opposite way, if it's directed from north to south instead of south to north, it can produce reconnections in the Earth's magnetic field that ultimately lead to energetic particles, electrons and protons, streaming back along the Earth's magnetic field line into the atmosphere and producing the aurora.
Wow, that's terrific.
Right.
Doug, did you want to jump in there?
Well, I was going to say, in addition to the aurora, that when the coronal mass ejection slams into the Earth's magnetic field, that magnetic field that does protect us from the radiation storm, that changing magnetic field causes problems for customers. That's why the Space Weather Prediction Center is monitoring the sun 24 hours a day to provide forecasts and get out those official watches, warnings, and alerts to customers, because when that coronal mass ejection hits the Earth, currents are being induced into the power grid. So the power system operators, with as little as 15 minutes of warning, can protect their systems by making sure they have sufficient capacity to handle the extra currents, to have people in place to turn off a transformer if it starts to overheat. So it's something industry can respond to. They just need to have the watches, warnings, and alerts to make sure they're able to.
Now, this one, if I heard you correctly, started less than an hour ago. And
that's right. And the solar
and so you weren't really able to get out. Your prediction is at what stage compared to, let's say, weather forecasting? What stage are you at predicting?
Well, I think the canonical thing people use is we're about 30 to 50 years behind weather forecasting. There are certain things where we're much better than that. With a coronal mass ejection, we can observe them back at the sun, and then we can predict with, in fact, a numerical model that we introduced on the Weather Service supercomputer just a couple of months ago. We can use that to predict when this coronal mass ejection would arrive at Earth. And the storm that erupted on Sunday, January 22nd, erupting at 11 p.m. Eastern Time, slammed into the Earth at 10 a.m. Tuesday, within an hour of when it was predicted.
And the one that's predicted started an hour ago, when is that going to slam into the Earth?
Well, the early indications are that, in fact, it won't. Because the active region has rotated away from an unfavorable position, that coronal mass ejection is going to fly harmlessly off into space, maybe hitting a science satellite or two on the way.
Mm-hmm. And I think a lot of people don't realize that the sun actually rotates.
Yeah, the sun
spins
rotates
on its own axis. Yeah.
Every 27 days on average, and because of that rotation, and I'm going to give Dave the opportunity to jump in here and talk about why that's significant. That's one of the reasons why the sun is so interesting and we have a solar cycle.
Yeah, part of it is that because it's a ball of gas, it doesn't have to rotate like a solid ball. In fact, it doesn't. At the equator, it rotates once in about 24 days. As you get near the poles, it takes about 35 days. And so that produces a shearing motion that things get stretched out and wrapped around the sun because of it, things like magnetic fields in particular. And that's, in fact, a key part of how the magnetic fields are generated and maintained within the sun is this what we call differential rotation, the fact that the equator is rotating faster than the poles. There's a shear layer near the surface that as you start at the surface and move inward, the rotation speeds up, then stays constant through 100,000 miles or so, and then changes again at a layer about a quarter of the way into the sun. So that rotation, in fact, is key to producing the magnetic fields.
Mm-hmm. 1-800-989-8255. Let's go to Virginia in Flint, Michigan. Hi, Virginia.
Hi.
Hi there.
Fascinating stuff. We've had a really warm weather here in Michigan. Is this going to impact weather patterns? Like, are we going to have a really hot summer now? Or another question is this going to melt the melt the ice packs and ozone and all that kind of stuff? I don't know if I've missed some of the answers already. But I'd be interested in how much it's going to melt, the ice that's already melting so fast.
Okay, Virginia, thanks for calling. We'll see what we can do.
Thank you.
Mm-hmm.
Yeah, those are great questions. That the sun does influence climate to some respect, but probably not weather as far as the day-to-day. That even though the sun got 100 times brighter in X-rays, it hardly got brighter at all when you add up all the energy that the sun puts out and the Earth receives. That's a tiny amount, even over the course of a complete sunspot cycle. When you go from no sunspots to 100 sunspots on the sun and all of that activity, the sun's only about 1/10%, 1 part in 1,000 brighter. And so it's a small change. Has again in the long run has a bit of an effect on climate, but day-to-day weather probably not.
Mm-hmm. Here's some questions, a few questions, different questions, basically the same theme coming from the internet, and people want to know how this would affect, a flare like this might affect people in space, either the space station or astronauts on their way to Mars or maybe on the moon, things like that.
Sure. Well, there certainly can be impacts. The astronauts on the International Space Station right now have to be concerned, but in general, do they need to be concerned from the activity that's happening right now? Not really. Their action, they would react at very, very large levels of radiation. There's a certain risk that they're willing to accept, a few extra or a slightly higher risk of cancer as they age, but the systems that they're using can be impacted by a radiation storm. So, with the shuttle, for example, the robot arm couldn't be used when a radiation storm exceeded a certain level. So there are certain impacts they do have to be aware of.
Tell us about this huge solar storm the storm of 1859, Doug.
Well, 1859 was it's kind of our perfect storm in solar physics. So the day was Thursday, September 1st, and Sir Richard Carrington was in his house at his observatory watching the sun like he did every day, and he projected this image of the sun with his telescope till it was about 11 inches across, and each day he would draw the sunspots. And this particular day he'd finished drawing the sunspots and he was just about to start measuring the locations on the sun when all of a sudden two bright lights appeared in the middle of one of these magnetic regions he'd measured. And he'd never seen this before. And he thought, oh, there's something wrong with my equipment. And he checked it out and quickly realized, no, it's not my equipment. And the careful observer that he is, he wrote down the time, 11:20 a.m. He was so shocked by this, he ran off to find somebody to help verify what he was seeing. He couldn't find anybody, came back, and it was already fading. It lasted all of 5 minutes. By 11:25 a.m., it was done.
Let me just interrupt and say this is Science Friday from NPR. Talking with Doug Biesecker, spinning a yarn about the solar flare of 1859. Keep going.
So now he knew something special had happened, and what makes this really remarkable is at a magnetic observatory. Again, when you shake the Earth's magnetic field, if you and I had a compass, it would point to solar north. But if you made a compass that was sensitive enough, you would be able to see that magnetic field was shaking during one of these geomagnetic storms. And in fact, at 4 a.m. on September 2nd at the Magnetic Observatory at Kew Garden, there was a great magnetic storm. And Carrington said, a swallow doesn't make a summer, but there seems to be a connection here. So in just 17 hours after he saw a flare on the sun, we had a huge, in fact, the largest ever recorded magnetic storm on the surface of the Earth. It was so strong, every magnetic observatory in the world saturated except for one that we know in India, and all measurements of that storm are now based on that one.
And what did it impact?
Right.
Telegraphs and things like that?
Right, so the technology of the day was telegraphs. So that's really where most of the impacts were. In Pittsburgh, the telegraph machines got so hot the operators couldn't touch them. In Philadelphia, a telegraph operator received a shock from his equipment. In Boston, there was a flame of fire. In telegraph stations up and down the East Coast, wood got scorched, paper burned. What did the average person see? Well, aurora. In Indianapolis, the aurora was so bright and so strong, you didn't have to look north to see the aurora. You could look at your southern horizon and still see the aurora. In Jamaica, it was described as like the light of a fire. It's believed that, in fact, it's been recorded that sailors saw it just 12 degrees north of the equator, and that if weather conditions had been favorable, it would have been seen even at the equator. So the entire globe was able to see the aurora on September 2nd, 1859.
Wow. Do we know why that happened in such a spectacular fashion?
Well, this particular event was really just the extreme of exactly what happened just this past Sunday. Associated with that solar flare was one of these coronal mass ejections. The speed of the coronal mass ejection doesn't tell you exactly how strong the storm will be. For that you need to know the magnetic field in the CME, but it's a pretty good indicator, and that transit of 17 hours is the fastest ever recorded, and the impulse, the amount of energy that got dumped into the Earth's magnetic field was just incredible.
Do we have a number you could put on even a solar flare that this happened this week? How big an explosion goes on?
No, I don't have a
Dave,
number that I could.
Well, typical flare, if you look at the radiant energy from it, is the equivalent of 1 million megatons of TNT. So that's the energy equivalent of 10 million Hiroshima bombs.
Wow. All right, we're going to let that sink in for a little bit. Take a break. We'll come back more and talk with Doug Biesecker and David Hathaway about the sun and solar events. Our number 1-800-989-8255. You can tweet us at SciFri. Stay with us. We'll be right back. This is Science Friday from NPR. I'm Ira Flato. We're talking about solar flares and the sun with David Hathaway of NASA's Marshall Space Flight Center in Huntsville and Doug Biesecker of NOAA's Space Weather Prediction Center in Boulder. And we're going to talk a few more minutes because I want to recap. If you just tuned in, there is a big solar flare happening right now in the sun, and maybe we can recap it. David, you want to take a shot at it? Or Doug, who would you like to tell us what's going on there now?
Well, Doug's probably better at that. He's on top of it.
Okay, Doug,
sure.
Bring us up to date.
Right, well, I was on top of it until I walked into the studio, but what we had on a scale of 1 to 5 remeasure space weather, and the solar flare we had last Sunday we measured at 2 on our solar flare scale, or an R2. The flare we just had is even larger at the R3 level. Within 20 minutes of that solar flare erupting, we started to see radiation particles at very high energies that are starting to hit the Earth. The Space Weather Prediction Center, in our role, of course, put out a warning as soon as the flare began, and in fact put out warnings for the radiation storm before the particles even began to arrive.
Mm-hmm. And that happened today?
So that's happening right now. So the flare itself is probably practically over.
Yeah,
the radiation storm will continue. It's hard for me to estimate without having seen the data recently how long that will continue. But what that would cause, potential impacts to that, when the radiation levels reach sufficient levels, those same particles that David talked about coming down and hitting the polar regions, causing the aurora, that also causes the high-frequency communications outages in the polar regions, and so any airplane flying over there loses their high-frequency radio. The problem there is they can't see those satellite communication satellites sitting over the equator, so in fact they have absolutely no way to communicate if they're in the polar regions during one of these storms, which is why it's important that they get the information as quickly as possible, because if they have to divert one of those routes, it's not very cost-effective.
David, do you want to add anything?
No, it's just I wanted to mention that I am in my office, so I can see the data, and the X-rays are well on their way going down, but the energetic particles, the protons in particular, are rising rapidly.
Here, reaching us on Earth.
Yes. These are being measured as we speak at satellites in geosynchronous orbit.
How many watchdog satellites do we have out there?
Well, NOAA, those same weather satellites that are taking pictures of the hurricanes, we have space weather sensors on those, and in fact the flare and the radiation storm are being measured with instruments on those same weather satellites. But we do leverage assets from NASA, for example. The coronal mass ejection that's associated with this flare, we know it's headed nowhere towards Earth because we've got images of the solar atmosphere from a NASA satellite that show us that that's what's happening. And we also use those data to help forecast when those coronal mass ejections will hit the Earth.
Well, we'll be watching over the next hours, and people will, I guess, listen to Science Friday will know about it because this word is coming out. It happened within, just a little bit over an hour ago. And thank you, gentlemen, for taking time to alert us.
Thank you, Ira, for having us on.
You're welcome. David Hathaway is solar astronomer at NASA's Marshall Space Flight Center in Huntsville, Alabama. And Doug, thank you. Doug Biesecker is physicist at NOAA's Space Weather Prediction Center in Boulder, Colorado.